Good morning, everyone. Good morning. Thank you, Dave. Susan. Again, good morning to our first seminar of the fall season. And I'm not sure whether many of you picked up that we used to call this the first Tuesday seminar. And sometimes we actually would have the seminar on the first Tuesday of the month. And we've done this in cooperation with the Harbor and Estuary program for many years. We have decided to change the name. I don't know whether anyone picked up that we no longer call this our Tuesday seminars. We call it the Edward A. Ames Seminars. And for those of you that may not know, Edward A. Ames, better known as Ned Ames, he's sitting in the back row. He's the former chairman of the board of the Hudson River Foundation and someone that I've had the pleasure of working with for, I guess, over 30 years, Ned. And I would just like to say that not only has Ned been such a strong supporter of science everywhere, but here in the Hudson River, but he's been a real proponent of having our science get out to the world and get out to folks like yourselves here. And he's been the one board member who's continued to be at these seminars, seminar after seminar, year after year, always having great questions asked and hopefully enjoying the results of the work. So we're really very pleased and honored to be able to name the seminar series on his behalf. So thank you. Okay. So our Dave Ralston from Woods Hole Oceanographic Institution has the honor of being the first speaker under our new seminar series. And before I introduce Dave, I just want to mention again a few ground rules. For those of you that are on the webinar online, we're hoping that you can see us and hear us. We can't hear you. You can, though, write questions that we will take up at the end of the seminar. If anyone has any problems dealing online, you can either call here at 212-483-7667 and ask for Melissa, or email her at melissa@hudsonriver.org. But hopefully you're all logged in and doing fine. We have about 25 to 30 people here in the room today. It's a nice audience. Today's topic we're going to talk about, or Dave Ralston is going to talk about sediment transport in the Hudson River. We've been interested in sediment transport for quite some time, not because it's an interesting topic. John Ladd, Bryce Weissmuller here, our folks from, where's Frank Nitsche? People love sediment, right? I mean, you don't need a reason to think about sediment other than it's wonderful to track mud coming down the Hudson River. But there are some real management implications with sediment transport, dealing with the amount of sediment that wind up in channels in the harbor, the association of contaminants with sediment, and when we have extreme events like hurricanes and tropical sandies, particularly Irene and Lee, we have an overabundance of sediment that wreaks havoc on communities and winds up disturbing the ecology of the river. We've lost most of the submerged aquatic vegetation in the mid-Hudson, or the upper tidal Hudson, that seem to be related to some aspect of Irene and Lee. So we're very much interested in learning more about sediment transport, and in particular during Irene and Lee, we had a lot of sediment that went into the river. We're not sure exactly where it is. Dave Ralston is going to help us find it. Frank Nitsche from Columbia is going to help us find it, and some other folks. So this is one project that we're funding here at the Hudson River Foundation. In the spring, we'll hear more from Frank and his colleagues at Columbia. And also we have some work ongoing with Kevin Farley at Manhattan College, he's updating his contaminant model to include some of the sediment work that these other folks are doing. But so we're pleased to have Dave Ralston today here. Dave is an associate scientist with tenure. He got tenure earlier this year. Dave has been at Woods Hole for the last 11 years after getting a PhD from the University of California, Berkeley. He wound up at Woods Hole, and to our good fortune, is interested in the Hudson and interested in processes. We've had a close working relationship with Dave, not only on the work you're going to hear about today, but on some other issues in the harbor, such as the impacts of floating structures. So, name of the presentation, Linking Sediment Transport in Hudson from the Tidal River to the Estuary, or what happened to all the mud from Irene. And I was talking to Dave earlier today. Again, what we think is really important is getting the questions right. The answers, we'll see how he does. But Dave Ralston.
Yeah, that subtitle was added on the train down here, just for Dennis's benefit, and just so I can tell him that I'm not going to answer that question today. I'm going to give an answer, but not the answer to that question today. Yeah. Okay, yeah, so this is looking at sediment transport on the Hudson, and we've done a lot of work in the past in the estuary itself. And I worked some with Rocky Geyer, and he's been funded by the Hudson River Foundation for decades, and then I've been fortunate to join in. We've done a lot of work down in the lower estuary and even the upper estuary, looking at sediment transport processes there. What I'll do now is sort of extend what's happening all the way along the river. The sediment comes in, most of it comes in way up here by Albany. It also comes in side tributaries. And then how does that, the fact that it has to go through a fairly long region of freshwater that's tidal is important to how, so what the fate of that sediment is, and what the time scales for delivery of sediment to the estuary and then ultimately to the coastal ocean. I want to start by, again, sort of acknowledging co-authors. A lot of this work is with Rocky at Woods Hole, but then also John Warner at USGS Woods Hole has been really instrumental in developing the model that we use. And then Gary Wall at USGS in Albany, Water Science Center, New York Water Science Center, was instrumental in making a lot of observations, which are actually critical because with many of these models, there's so many uncertain processes and nonlinear factors that you need to have observations to constrain them to believe them at all. And fortunately, in this case, we're, I think, sufficiently constrained that we can believe the processes that are going on in the model and then draw conclusions from that, which we can't do from the data alone. So just as sort of, again, sort of, most people probably know this, but just for reference, for where are we talking about? Of course, we're down here in New York. I'm calling that sort of, I'm going to reference a lot of sort of distances along the river. And so that's zero, that's the center of the universe. And then we work our way up. There's the tides go all the way up to Albany, which is 240 kilometers. Typically, during low discharge conditions, the salt can move farther into the system, into the estuary. And so during sort of summer low discharge conditions, we end up with salt up around Poughkeepsie, 120 or so kilometers. During higher discharge conditions, essentially the river flow pushes the salt out into a much more shorter, more stratified system, and you end up with sort of the salt ending up somewhere sort of in the 30, 40 kilometer range. Again, that's sort of during extreme high flow discharge periods. And so what I'm showing you in the background, you probably realized already, is a satellite image from a couple of days after Tropical Storm Irene came through. And you can see the coloration. So fortunately, like the sky is cleared with the satellite image. You can see the discoloration of the water associated with suspended sediment. So then, for reference, that with Hurricane Irene came a lot of rain. We'll get into just how much. But as it's associated with that rain, was discharging the river. That discharge in the river pushed the salt down toward the mountain. And that transition went from about 100 or so kilometers down to about 40 kilometers over the course of a couple of days. And again, I'm going to hopefully convey to you the importance of sort of our baseline case. The salinity is tremendously important for how salt moves through an estuary. And we're going to layer on top of that how what happens in tidal freshwater is important as well for how sediment moves through the entire system. Okay, so if we zoom in a little bit, we see some nice features down in the harbor itself. You can see, I guess, to me what's striking, you can see the discoloration here. that's associated with a flood tide, tidal intrusion front. So this is relatively lower salinity ocean water moving into the estuary, the lower harbor. You do see a lot of discoloration of the suspended sediment down in the along Manhattan. A lot of news stories. A lot of people are pretty excited about it. But if you go up the river, you see it's actually much more brown, almost like a reddish brown. It's a different color, much higher concentration. This is up in Haverstraw Bay, about 60 kilometers up. Again, a couple of days after the storm occurred. So we'll come back to sort of how well this sort of came. We were sort of seeing these same sorts of features in our models themselves. Okay, so yeah, so a little background on tropical storm Irene and then Lee. So there were two tropical storms that came through in 2011, summer of 2011. Lee sort of tracked up the East Coast, and it was a hurricane and turned into a tropical storm just before it hit made landfall. Dumped a lot of rain sort of in this region. 7 days later, tropical storm Lee came up in the Gulf, curved around this way, and dumped a bunch of rain in the same region. So this is the cumulative rainfall over that, I think, 10-day period or so, 2-week period maybe. And so the important point here is that there's an epicenter right there, which is sort of midway along the tidal Hudson. This is actually, there's a watershed here that drains to the east. It's called Catskill Creek. And there's a watershed which drains to the north, up into the Mohawk, called Schoharie Creek. Thank you. And so this is where you had the 20 inches of rain over the course of essentially a week. And everywhere else there's a lot of rain. It's not 20 inches. And so the result was, with all the increased precipitation, you have loading of the streams, higher sediment concentrations. And so this is an image that Gary Waltz took from the Mohawk. This is after that input from the hose has been diluted. The hose accounts for a few percent of the total watershed of the Mohawk. And yet you see over 2 grams per liter, which is a phenomenally high concentration of sediment coming in to the tidal Hudson at the upstream end. Again, this study was possible in large part because by chance, a few months before these events happened, New York DEC and USGS put in gauges on a lot of these, and the River Foundation was instrumental in this as well, put in gauges on a lot of these side tributaries. And so we actually have not only discharge, which is a standard measurement, we also actually are measuring suspended sediment or backscatter turbidity at each of these locations. And so with concentration and with discharge, you can get a flux, a volume flux. And so what I'm showing is several of those river inputs which were actually gauged during Irene. And so the Mohawk and the Upper Hudson, again, so most of that precipitation happened over the Mohawk watershed. And so the Mohawk accounted for cumulatively over that 2-week period, almost 1.5 million tons of sediment, new sediment coming into the system. Can you hear me okay? But I've put the numbers here as well, sort of what fraction of the total watershed area that represents. And so in theory, you know, if you're just looking at sort of the watershed area, you expect that to scale with the freshwater input, but then also the sediment input. That's certainly not the case here. So the Mohawk counts for 30% of the watershed area. We put in 1.5 tons, which when you add everything up, you've got to almost 3 million tons of new sediment. So the other huge contributor was Catskill Creek, which, as I mentioned, was the epicenter of where the precipitation was occurring, and that little 3% of the watershed area accounted for 0.7 million metric tons of new sediment coming into the system. Like I said, we had measurements at several other locations along the river. We come up with a reasonable estimate of what the total input was to the tidal river from this storm over that period. 3 million tons, for reference, sort of a long-term annual average for the Hudson is about 500,000 tons. You got almost 6 years of the sediment in a 2-week period, new sediment in the system. So the big question is, where did it all go? Okay, so another sort of conceptual framework piece we need to have is that estuaries are great traps of sediment. This has been known for decades, if not longer, centuries perhaps. And so why is that? Well, so there's important processes, and I'll hopefully highlight those here just for reference so you can interpret how the actual event happened. But this is a highly schematized, idealized estuary. So we have the ocean at the left side, the freshwater river coming in at the right side, and we have a salinity gradient. High salinity over here, low salinity here. That leads to stratification. It also leads to an estuary circulation. The estuary circulation is the salt water is denser than the freshwater. Salt water tries to move up the estuary to bed. Freshwater tries to move out the estuary to the surface. The reason that's important for sediment is sediment is heavier than water. So sediment wants to sink to the bottom. So sediments may preferentially move up estuary. Once you get up into the river, there's not that estuary circulation. You have only downriver flow, unidirectional seaward flow. And so as you can see, there's a convergence of suspended sediment at somewhere near the limit of the salinity intrusion. Like, it leads to higher concentrations. That leads to higher rates of deposition in that region of what we call the ETM, which is the estuarine turbidity maximum. So the maximum in sediment concentration associated with the salinity intrusion. Another important thing I mentioned is being stratified versus unstratified. What stratification tends to do is it tends to reduce turbulent mixing, because essentially you have to lift heavy water up in order to mix it. So it takes more energy to mix the heavy water, which means there's less energy reaching the bed and available for resuspension of that sediment. So you have greater stresses, bed stresses are what resuspend sediment in the river than in the estuary, and that also reinforces this accumulation of sediment at the ETM. So it's a combination of the estuarine circulation and the stratification gradient. So does the Hudson at all look like this cartoon? And as I mentioned, a lot of this work has been done both with NSF funding, but also with Hudson River Foundation funding. So it goes back several decades. This is looking at down near the George Washington Bridge, where we've known for a long time that there are really high sediment concentrations. Well, why is that? One thing that these are observations of newly deposited sediments. We use beryllium-7, which is a marker of recently deposited sediments, a geochemical marker. And you can map out sort of where the new sediment went, in this case, within the last few months. And so what they found was, in June 1998, June 1999, similar deposits of a lot of new sediment, tens of centimeters of new sediment, were located near the just north and south of the George Washington Bridge, which is consistent with there being high sediment concentrations there. This accumulation can happen very quickly. This is actually using an in situ sensor of an instrument which is moored right here, looking down at the bed and just measuring how far the bed is away from the instrument. And so what it found was over the course of about 10 days or so, you had 12 centimeters of accumulation at that location, which is again an extremely rapid increase in sediment at the bed, and it corresponded with what we could see in laminates in a core, in a push core. So this went into building a conceptual model for sort of how sediment moves through the system. The spring freshet's really important, so that the annual discharge cycle is there's snow up in the Adirondacks. That snow melts, increases the river flow. That delivers a lot of sediment. That sediment comes down into the estuary, and then a lot gets pushed way down in the estuary, and then it works its way back up and deposits sort of months after the freshet. And that sort of was the conceptual model, an annual time scale. As I mentioned, there are high sediment concentrations in this region near the George Washington Bridge. It's almost a gram per liter, which is tremendously high it's very high concentration. But the important thing to note here is that it's not at the limit of the salinity intrusion. The black colors are the sediment concentration. The numbered contour lines are salinities, and so we're sort of at intermediate salinities. And so this is 15 or so, which is intermediate. So that's somewhat in contrast to the bigger scopes of the model of trapping at the limit of the salinity intrusion. Well, if we work our way farther up the river, we can go up to Haverstraw Bay, and this is actually an image from one of Frank's papers. And what he has shown is that there's high rates of deposition up in Haverstraw Bay. This is deposition over the last, I believe, many decades, 70 years or so. But in any case, and there's also high rates of dredging up here. They have to dredge to keep the channel open. And so there does seem to be a lot of accumulation of sediment up here. It's also near the limit of the salinity intrusion. So we had some observations up there. And we made some time series measurements of sediment in the channel. And this is showing over about 5 days. The dark colored regions are flood tides. The light colored regions are ebb tides. As we can see, they're relatively high concentrations, a couple hundred milligrams per liter, or 0.2 grams per liter. Not as high as further seaward, but still fairly high. And what we note is that these spikes that occur during flood tides correspond with a salinity front moving past. So the dark green line is the salinity at the bottom. And so what you see is that as you sit at a point, the salinity increases rapidly. Corresponding with that, the suspended sediment concentration increases rapidly. And so what that is an accumulation of sediment at that front, which then is convecting past you. So that's consistent with the trapping conceptual model associated with the estuary circulation. We also note that during periods when there isn't salt there, because again, salt's moving up and down with both the discharge and with the spring heat cycle, we see a much higher concentrations during the ebb tide. So when there's salt there, concentrations are much greater during the flood than during the ebb, leading to a net landward transport. When there's not salt there, there's higher stresses, there's no stratification, and so you have more resuspension of that material during the ebb. So reinforcing that both estuary circulation and the stratification which lead to trapping in the estuary. Okay, so that was all sort of why the estuary matters. We knew that already. What happens to sediment when it goes into the tidal river? Big picture, a lot less is known about that. A lot less has been done on sediment fluxes in tidal rivers here or anywhere else in the world. That being said, we do know it's important in the sense that there are many of the major river systems, many of the systems which deliver the vast majority of sediment to the continental margins, have very long tidal reaches without any salt. The Amazon at 600 kilometers, many of the other systems hundreds of kilometers, like the Hudson. There's also been very back-of-the-envelope hand-wavy estimates of that roughly a third of the sediment which is gauged, usually you put your gauge at the limit of the tide, because it's hard to gauge when the water's moving back and forth. And so if you measure what's coming into the tidal river, roughly a third of that never makes it to the coastal ocean. Instead, it's being sequestered in the tidal river, in the floodplains of the tidal river, and so forth. Again, that's a very poorly constrained number. And so conceptually, important processes we need to keep in mind here are that while we have a river, so we have a mean flow associated with the freshwater input, we also have the tidal portion. And in most cases, those tidal velocities are much greater than river velocity. In the Hudson, some nominal numbers are sort of 0.5 meter to 1 meter per second tidal velocities, whereas river velocities are more like 5 centimeters per second during moderate to low flow, on up to, as you'll see, 40 centimeters per second during Hurricane Irene. So a lot less than tidal velocities. The important part of the river discharge, though, is it only goes in one direction. Tide's going back and forth, so it's not going to create, at most simple level, it's not going to create a net transport. So you need the river flow to have a net transport seaward. And then finally, the important point here, is, which we'll sort of come back to, is that the river discharge controls the supply of sediment. The tides in the river combine to control the transport, but the river discharge alone controls the supply. Okay, so back to Irene. Again, we're sort of, for big events, you can never sort of plan out field programs for them. You can't sort of anticipate when they're coming sufficiently. In this case, we were lucky to have some gear in the water, or not us, we took advantage of other people's gear in the water, which was in the right place at the right time to make measurements that you can then use to analyze the system. So there wouldn't be the places you'd ideally choose to put measurements for this type of event. That being said, they're really useful. So I mentioned the gauge discharges from USGS and various tributaries. They also had a measurement at the Poughkeepsie, which is halfway out. Typically, sort of the salt never gets past there. And that measured the tidal volume flux, so how much water is going back and forth. It also measured suspended sediment, sort of. And so we can get a measure of the total flux past Poughkeepsie in the tidal river. We also had turbidity sensors, the Reef Coast Network, which is funded part by the Hudson Foundation, and there are a lot of sort of surface sensors of sometimes salinity, sometimes turbidity, water level, and so forth, so we're able to access those. So look at how sediment moves down from the system during the event. I also mentioned we used a model, and this model has been in development for over a decade. and it keeps getting, but in development, we have more processing power, and therefore we have more refined, and we have a bigger model, and we have more inputs and so forth. So it's certainly changed a lot over that period. One of the big sort of changes we had to make to adapt to this problem was to increase the size of the grid. The grid used to stop now with the battery because we only cared about the estuary. During high flow events, a lot of what happens down in the lower estuary, the upper harbor and lower harbor, is important for how salt moves around, how sediment moves around. So we had to expand our grid, which is computational costs and so forth. We also refined it spatially because we found that resolving those salinity fronts I showed in the time series is pretty important to how sediment gets trapped in the estuary. We had the inputs from the various new sediment. We also had, and this is really important, Frank's work mapping out bottom composition. So he basically used acoustic measures and cores, grab samples, to characterize almost the entire Hudson, and made these sort of shape files that map out different types of, is it muddy, is it sandy, is it sandy mud, is it muddy sand, and so forth. We then took that data and turned it into a bottom boundary condition, which this is probably getting too much in minutia, but this is really important as far as being able to have a model to trust. We did a fair bit of sort of evaluation of the model. I won't spend much time on this, but again, we sort of used the sensors that were available. We were able to show the salt field evolved as we expected to. We were able to show the sediment pulse. So this is showing suspended sediment, actually turbidity and suspended sediment for the model. You see the pulse associated with Irene and with Tropical Storm Lee, as they move down through the system. And I guess the other sort of key element here is sort of going to kind of come back to the uncertainty of the problem is what you adjust is the sediment characteristics for how fast the system is settling velocity. And so sediment wants to settle, it settles really quickly. Fine sediment stays up in the water on the moves faster. And so what turned out, what worked best for this is to have really slowly settling particles. So, which makes sense. There's a lot of new fine sediment coming into the system, which is then sort of essentially being carried down at the rate of fresh water. Okay, so the important thing, where did the sediment go? This is showing a couple time series from Poughkeepsie, and these are actually just observations from Gary Wall, and then also the inputs we had from the various USGS missions. The inputs are in black. So the top panel is river discharge, the bottom panel is cumulative sediment flux, so how much total sediment is coming into the system over this period. And then the red is what we observe at Poughkeepsie. So you can see the fresh water, which is the volume flux, very quickly goes past Poughkeepsie. It doesn't take long for that floodway to pass down from the upper tidal on out to the ocean. However, the cumulative sediment flux we found was a lot less than the total. The total is almost 3 million metric tons. The total past Poughkeepsie after a couple of months, after a month and a half or so, was just a million metric tons. The model agreed with this because we made it. So yes, volume flux, conserving mass is very easy in a model, so that we didn't have to do anything for that. But then the sediment transport was essentially, it depended on the settling velocity, very finely settling particles. And so this is sediment that's moving really fast. This is not like assuming this is really heavy particles getting stuck up in the watershed, up in the Tidal River. This is really fast moving sediment. And yet still, we barely get that much, essentially, a third of the total sediment passing it. So where did the sediment go? And so this is actually a little bit different look, so hopefully we're able to do this. On the y-axis is distance along the river from the 0 at the battery up to 240 at Albany. It gets you about halfway up. And then on the different lines, different colored lines are different snapshots in time for where the new sediment is. This is only new sediment from the watershed that came in with the storms. And so what we see is sort of the rainbow color sort of progress in time. And so we see at the start of Irene, there's a little bump here that's associated with that input from Catskill Creek, which arises very quickly. It's a short watershed. So there's a lot of comes in sort of near the source. There's also a little bit coming in from over the dam from Mohawk. After a couple days, so this is at the end of Irene, there's a big flux of sediment up the upper river. And then, since after what, 3 days, I think? If we then advance a little bit farther, this is sort of before Lee and then after Lee. You see another big pulse of sediment coming in, a lot of being trapped in the upper tidal river, north of the Estuary. We also begin to see accumulation of sediment down in the Newburgh Bay, which is a consistent theme. And we see accumulation of sediment in the estuary itself in Haverstraw Bay, which we previously identified as a trapping zone for the estuary. And then finally, for this set of slides, a month after Lee, you start to see some of that sediment which was previously trapped in the tidal river begins to work its way down. The red lines are lower than the yellow line. There's more accumulation in Newburgh Bay especially, and there's more accumulation in Haverstraw. And so we do see this high rate of deposition in the upper ETM, but the bulk of the sediment is still, so 2/3 of it is north of the Kitsey. Another large part of it is still trapped up in the Newburgh Bay as well. Okay, so if we instead change that to map view, which is a little more considered perhaps, this is showing sort of distance along the river from Battery on up, and then we loop around here to get on the same page. This is Newburgh Bay. This is moving on up the Tidal River. We see high rates of deposition, particularly over on the shoals of Newburgh Bay. You see the high rates of deposition in the channel of Haverstraw. Not much happening down in the lower estuary, again after a month or so. This is again, we didn't have any ground truthing to verify this, but with Frank has his measurements of deposition. This is again totally different apples and oranges, but there's a lot of similarities as far as where the deposition is occurring. This is a long time scale. You see lots of deposition over on this western side of Newburgh Bay. And that's the same place we see this sediment getting put down associated with that region. Okay, so speaking mechanistically, what's happening? Where's the sediment going? How's it moving through the system? This is showing a time series. I'll orient again. So on the x-axis in all these is time. The top panel shows the river discharge of the two storms, and the gray is the tidal velocity. And again, to turn back, the tidal velocities are also important for resuspending material in the river and also for where the salt is in the estuary. This is showing time, distance along the river, and the colors are suspended sediment concentration. So this is the massive sediment, new input from the river, which is suspended up in the water column. And so we see these sort of bright red colors are associated with input from the Mohawk, and then this one is input from the Catskill Creek. This is with Irene. Same thing happens with Lee. High rates of input. But then very quickly, the concentrations decrease. We also see that the black lines here are where the salinity contours are for the 2 PSU and 5 PSU isohalines. So that's where the estuary is. The estuary starts about 100 kilometers. With a high rate of river discharge, it's pushed downstream, and then it rebounds during the lower period. It's pushed downstream again. And then you have neap tides, and during neap tides, the salt wants to move back in. There's not much mixing, and so you see the salt move back in. The important point here is you see very strong gradients. The new sediment is resuspended upstream of where the salt is, but there's not much downstream, which is trapping at the limit of the intrusion. So if we think about sort of how far did this sort of pulse get during the events last a couple days typically. And if you take sort of the total discharge, which is 8,000 cubic meters per second, which is roughly a 10-year storm, so a pretty big event. And you sort of turn that into a mean velocity, about 40 centimeters a second, over 2 days, you get to about 70 kilometers, which is about how far the sediment is associated with the pulse itself. After that, your discharge drops way down. You don't have that same effective force moving sediment through the system, so the sediment tends to get stuck there. However, as you read in the news, or you actually saw outside the window, people saw very high concentrations in the harbor and in the lower estuary itself. So where did that sediment come from? And so what we think happened there is that essentially it's resuspension of sediment which is already on the bed there. And why is there such great resuspension? Well, it's a combination of the increased river discharge, increased the bottom stresses, allow more resuspension, but also, more importantly, is because you push the salt downstream, you have regions which are often stratified and don't have high stresses because they're protected by the stratification. Suddenly they're unstratified, have high stresses, and so there's available sediment to resuspend and get ejected downstream. So you see that in the upper ETM, you also see that in lower ETM. So So there's lots of available sediment down here. It's just usually trapped in the deep western there. But instead, because you increase your stress and decrease your stratification, you see very high concentrations down in the estuary itself. And then once you come out, get out, so this is the similar type of pulse associated with Lee. As you get out here, this is just more the standard spring neap variability. During spring tides, you have resuspension in the lower estuary, and then during neap tides, the salt works its way back up, and then you have resuspension in the upper estuary. Okay, so this is the slide I showed before from where new sediment is showing up. What happened to the sediment which is on the bed? This is much more of a patchwork quilt, so instead of just having deposition in red, we have deposition and erosion, and so it gives the sediment from the bed. As we see, again, so there's high rates of deposition of new sediment, so sediment which was everywhere got remobilized by the high concentrations. Where did it deposit? It deposited in Haverstraw Bay, deposited on the shoals over here in the lower estuary, and deposited down in the harbor. There also was additional deposition up here in Newburgh Bay. Again, this is material which was up here in the Tidal River, which then deposited. And so, what you imagine is sort of a conveyor belt of sediment which was on the bed in the last storm, way up here in the Tidal River. It gets resuspended by the event. It gets pushed further downstream, gets deposited here, whereas the sediment which came in most recently gets stuck in the upper estuary. It's sort of a hopscotch, multi-step process to get down through the Tidal River. Okay, so can we sort of explain conceptually what's going on here, bigger picture? What's controlling how sediment is moving through the system, through the Tidal River especially? Well, so we know that sediment loading is a highly nonlinear function of discharge. So what this is showing is sediment load. This is for the Mohawk at Cohoes, but many river systems are very similar. What they show is that as discharge increases, the sediment load increases. And so it makes sense because the sediment load is just the discharge times the concentration. So the concentration stays constant and be linear. But as you get bigger and bigger events, the concentration doesn't stay constant because you end up eroding banks, you end up having remobilizing patches of sediment which had been sort of essentially not available before. And so your concentration goes up. As you get to higher and higher discharge, it's something like Q squared. So then, as you get to very high discharge, your total flux goes at something like Q cubed. It's a lower function when you're at moderate discharge, or before bank full maybe. Then you get the higher discharge, it goes to Q cubed. It's very nonlinear. What about for sediment transport in the system itself? What I'm showing here, again, is the same axes, it's just additional information. The river discharge on the x-axis and then the sediment flux in the estuary. And so I picked a point, which is just at Poughkeepsie, picking a point in the Tidal River from the model. The black dots are what we're putting in. Those are actually measured data from various watersheds. You can see that there is a very high rate of increase as you get high discharge. The red dots are what's happening to the new sediment at Poughkeepsie. And so there's a period when there's just not much new sediment around. There's not much flux. This is sediment flux down estuary. There's not much sediment flux. Once that new sediment flux arrives, it does increase the discharge, but it's not increasing as fast as the supply. So essentially what's happening is we still have the same issue of the river discharge is controlling the mean flow, but the concentration is instead of being controlled by the river discharge, it's controlled by the tide. The tidal velocity is a lot bigger, they control the suspension. And so they're independent of the discharge. And so, again, this is, I said here, it's massive oversimplification. But at first order, that's what's happening. We have a roughly linear dependence for the new sediment, and the blue is what's happening with the sediment which is on the bed already. And so it's behaving the same way. It's a little bit different gain function because there's suddenly this massive amount of new sediment around, so it's less supply limited. But you still have a lot of, essentially, this mismatch between the supply and the transport, particularly at high discharge. This is showing that same data in the time series form at different locations along the river. I was just showing at Poughkeepsie here. We instead look along the estuary. You see the red is what's happening with the new sediment, how much sediment is going past that location. And the blue is what's happening with the sediment that's already on the bed. The black line in the top panel is the input, and you'll note there's a vast difference in the axes here. This is almost an order of magnitude greater axes, axis limit than in the Tidal River itself. And so the important points here, you have these big pulses associated with the events themselves, including a pulse of this old bed sediment moving downriver. But once you get out into this period where the discharge is back to normal, you have very weak discharge. If you look closely, which we'll look closely later, you do actually see a little bump there, a little bump there, a little bit there. Those are associated with spring tide. During spring tides, you have greater resuspension, weak downstream flow, and so that you do actually have more sediment moving down the river. Just they're controlled by the tide. Okay, so if we take I'm not an oceanographer, even though I work at an oceanographic institution. I grew up as an engineer, and so if you take a really simple engineering approach to this, we call it a time scale for how sediment is moving through the system. This is vastly oversimplified. But so you think of it as the tidal river as this continuously stirred tank reactor, which it's not at all. But you think there's some mass of sediment in the tidal river. You have some flux out. You take the mass divided by the flux out, that gives you a time scale. Okay? So that's sort of the conceptual model we're working with here. And so we've done that for, again, sort of picking as a point for the tidal river to Poughkeepsie. In the top panel, we see the black is the flux in and the red is the flux out. And here, so we can see it, I've multiplied the flux out by 10. Remember, there's an order of magnitude difference in the axes. As we see the big events, we see this little event a little bit later on, and you see this increase during the spring tides. This is the total mass of new sediment above the Poughkeepsie, something like 1 million tons or so. Or actually, it's log scale, so it was 2 million tons. It decreased over time. And then if you take those two and you sort of divide by them, divide one by the other, you get a pretty noisy number, and it's log scale as well. But during the event, you have a lot of flux, not much mass up there, so the time scales are fairly short. After the event, you have sort of asymptote towards, a lot of mass being stuck up there, not much flux. And it's something sort of like an annual time scale for how long it would take if you had that flux to move it down the river. So the important point here is that this is really variable. These are pretty long time scales. And I think that these are probably an underestimate of time scale, because what we're not doing here is we're not accounting for how the sediment's changing as it sits in the river. As it sits in the river, no longer do you have just the fine stuff, you start to have more of the bigger particles. It starts to, form bigger flocks, and essentially it's hard to move down the river. You have sequestering of sediment in overbank areas and in stress refuges which we're not resolving in the model. Basically, sediment is easier to hide in the real world than it is in the model. And so I think if anything, these estimates sort of an underestimate of the time scale for sediment flux down. Okay, so as I said, those are really big events, and we wanted to. We had some observations these last couple of years, hoping to see another really big event, but we didn't see really big events. And so instead, we're going to look at how discharge affects how sediment moves through the tidal river. And so as I mentioned, so this is sort of the day of the year. The gray lines in back are sort of a climatology of what the flow in the Hudson is like. You have the spring freshets, which occurs sort of April, May time frame. You have winter storms, and you have these really unusual tropical storms, which just don't occur very often. And so what we had was sort of in the spring of 2014, is sort of a typical spring freshet year. And then last year, we actually had a fairly low discharge, very cool, as you all know. So we take a look at those as a couple of examples. So this data is all very, well, it's not that new, but it's new enough that we haven't spent enough time looking at it. It's all very preliminary. I can't go into much detail on this, but we just get some initial hints as far as what's going on and how the discharge is affecting how sediment is moving through the tidal river and then also the estuary. And so this panel here at the top is the river discharge. We had a moderate sort of 3,000 or so 3 meters per second freshet. The tides are in gray again. In the middle panel is the salt up in Haverstraw Bay. So we can see sort of that there's sort of when the discharge goes up, the salt gets pushed downstream. There's no salt there. When the discharge decreases, you get salt moving back up. This also depends on the spring neap variability, where during neap tides, you have salt moving back up. So we made measurement of suspended sediment. Well, so this is from the Stodak Island Free Coast turbidity sensor. We also had suspended sediment velocity measurements, sort of Tivoli, which is 160 kilometers, Newburgh Bay, which is 90 kilometers, and then Haverstraw, which is about 65. And so the bottom time series is the sediment, the turbidity measurement. You see a lot of variability, there's still some noise in there which needs to get taken out. But what we see is the black line is the pulse of sediment associated with this first flush, discharge of the season. You see it move past Skodak, move past Tivoli, move past Newburgh, and move down into the estuary. And so that's nice. It's almost exactly what we saw with Irene, however, it's the lower magnitude. The same processes you think are going on there. You also see down in the estuary a lot of variability associated with the spring leaf cycle, resuspension during spring tides, and then after the salt goes away. So we can come with a sort of time scale of flux down through there. We ran the model and it agreed, of course. And so this is sort of the same panel I showed on the Irene case. We have total sediment input in black, and we have the flux past Poughkeepsie in red multiplied by 10. You can see there's a lag associated with that pulse of sediment coming down from the system. It is correlated with the events, but also it's decreasing through time. And so this is just from that 2014 season, how much new sediment came into the system. And so the mass of new sediment stuck above Poughkeepsie was, it's an order of magnitude less, but a couple 100,000 metric tons. The time scale associated with that, again, are sort of, they start out during the events in sort of, a few months, but then you can't sustain those high discharges, and so you end up with more like a year to a few years to many years. Okay, so that was sort of like a typical spring freshet. Keep in mind, that's still a fairly short part of the whole annual cycle. It was just a couple months, 3 months or so. The winter 2014-15, so starting last December, we had observations at the same locations. The big distinction here is that there's much lower discharge. So the max peaked out sort of an early storm about 2000, and then the freshet came a little later, and it wasn't that big freshet. And so as a result, there's a lot more salt in the system. There's a lot more trapping of sediment up in the estuary, and you also have a much weaker sediment signal in the tidal river. So there's less sediment being put in. There's very little sediment coming past Skodak. You see a little bump here associated with this sort of event here up at Tivoli. But then, once you get down to Newburgh Bay, the signal is not river-driven, it's tidally. You see this modulation with the spring. These big concentrations here are spring tides. These concentrations here are spring tides. They're independent of the river. Sure. Yes?
I'm just wondering how the fluctuation in sedimentation affects the growth of plants and animal life. I don't know.
Everyone wants to talk about fish and dolphins. Sure, oysters and dolphins. So I think there's a lot of people can talk about this better than I can, but certainly there's been an observation that as you have greater turbidity, you have less light availability, which potentially affects the growth of submerged aquatic vegetation. You could have burial of sessile benthic organisms. I think, yeah, I won't say any more than that about that. But, so that is sort of a question, I think, which is a little bit, which hopefully we can address in some of our data, with some of the longer-term sensor data. How has this increased loading of sediment associated with the event changed the background turbidity? And sort of what the typical tidal resuspension is. Which we see that in the model for sure, because essentially there's greater availability of sediment. And so the question is, to what extent? I think that is true in the real world. The question is, to what extent is that, and then how does that affect it?
Okay, good study done in the future.
Probably. Yeah, we'll think about that. We'll come back to that later.
Okay. Okay, so then just wrapping this piece up, the key message here is that much lower discharge, you have a lower input, but you also have much lower fluxes downstream. You get very weak velocities. And so as a result, your time scales become very long. The time scales for sort of their total mass of sediment, even though there's not much mass, the flux is really weak, and so we're talking years to decades. Okay, so the last thing I want to say is that this is sort of showing that image again of sort of where sediment is with the new sediment, and then also the sediment that was unbed already, the time series. And the point I want to make here is that it's not just storms, it's actually the timing of the storm matters. So this storm was an unusual summer, well, some hurricanes happen in summer, but they don't come up here very often. And so you had a fairly low flow period, and the salt was pretty far in to start. Whereas we usually expect storm events to happen in our easters during winter when there's a higher discharge background, the salt might be expected to be further downstream. So where the salt is affects how far, as you can see in this image pretty clearly, where the salt is affects how far sediment from the river can affect into the estuary, which then affects also how far sediment, which is in the estuary, can get affected out to the ocean. And so this is just an example. This is from a totally different data set where we did some, used a much simpler model that used data for the last 100 years of the Hudson. And essentially try to characterize the variability with the actual time series of conditions. And so what I'm showing here is for a location down near the lower ETM. This on the y-axis is essentially the sediment transport capacity. Positive is you have sediment moving up the river, and then negative is you have sediment moving down the river. And on the x-axis is discharge. So during low flow, you have sediment moving only up the river, which is, again, that trapping estuary. During high flow, you have sediment moving seaward. And I picked off some events here. This happened to be the big events, and this actually was done before Irene, so I don't have Irene on here. But the point is still made because the size of the dots here represent whether it happened during a spring or a neap tide. So bigger dots occurred during spring tides, and smaller dots happened during neap tides. During neap tides, there's not much mixing. The salt will work its way all the way up in the estuary, and you have a large region which has to get pushed out by that discharge event before you can start exporting sediment. During spring tides, there's a lot of mixing. Salt's already been pushed out, and so the event itself doesn't have to push sediment very far to get it to the coastal ocean. And the key point being here is that the time scales of events, a couple days, are short compared to the time it takes for the system to respond. And so even though you have a big increase in discharge, the estuary doesn't feel that. And so instead, what its initial condition was affects where the trapping is coming from. Okay, so just to summarize, the key points here that the sediment load of the system, because there's this mismatch in scaling, scaling of the load and the transport of sediment, Q versus Q of the first, the input greatly exceeds the transport capacity associated with the event themselves. So you get up to 80% of the sediment trapped in this tidal river associated with the event. The event is important for remobilizing sediment down in the estuary, which has implications for organisms, but also for potential contaminant transport. But it also depends a lot on the phasing, both seasonally with discharge and then during the spring deep cycle, as far as where the salinity is that fosters the capsule sediment. And then finally, this is, I think, was the most striking result of this study was that the time scales associated with sediment moving, from the watershed to the coastal ocean are a lot longer than we thought previously. We used to think it was, months, weeks to months. So the sediment which came in with the spring freshet in April or May went down the harbor in May, and then worked its way back up the system in June, July, and August. It looks like in this study that the time scales are a lot longer than that. Yes, there is new sediment coming in with those events, but that sediment was already sitting in the tidal river for years to many years. And then so I sort of alluded to this a little bit, but a lot of these processes are hard to constrain. There's a lot of uncertainties, and they're hard to constrain in the policy. As you go to longer time scales, it becomes more uncertain. And this is where I think using sort of other tools, the characteristics of sediment itself, to sort of map out where something is coming from and how long it's been there is a useful pair to this process-based model. Happy to take any questions. Oh, and I should take my funding from Pure Foundation and Henshaw.
Questions?
Three. Having two great effects, both because of the proportion of smallest sediment should be higher in the first event than the second event. You pick that up. Second question, so you practice Sandy on something like this kind of external, not so much associated with rain. How would that be the sediment transport? Third is interfere with Johnson, not positive, but most will shoot down by the harbor here. It's probably more than quiescent there, where things relatively settle out. You see that.
Those are three great questions. I can answer them all.
Maybe repeat the question.
Yeah, so the questions were, So the sequence of two events in a row, does that affect size distribution, sediment size distribution, fine sediment versus coarse sediment? And we can't really answer that because we don't have any sediment size data. One thing we do know, one sort of corroborating point to very high, very low swelling velocities, which means very small particles, is that I mentioned that USGS used an acoustic measure to measure sediment concentrations at Poughkeepsie. And that approach totally failed because as you go to small, finer particles, the calibration changes, and they weren't calibrated for that. And so instead, we had to use an optical backscatter. It's kind of technical, but basically the point is it's consistent with the particle sizes being much finer than are typically around. And so I think that there was, and I think it's probably more characteristic of the geology of where the events happened. So I think we'd have a hard time picking up variability between the storms, but I do think we're pretty confident that that new input was much finer than the stuff that is usually around. The second one was Sandy. So Sandy is an interesting contrast because obviously the impacts were big around here, but from the sediment transport point of view, they weren't, particularly for the Tidal River, there wasn't much happening. And so because there wasn't this great increase in supply, if you had a certain amount of resuspension associated with the storm surge itself, you had a lot of coastal processes going on. But from the Tidal River point of view and from the estuary, it's not new. It's a bit of
flushed out some of these stuff.
so the discharge just didn't pick up that much. It was mostly it's a dry storm, a lot of wind, but not much rainfall in this basin. So it's acute. Whereas Irene, a lot of rain and not nearly as much wind. So it's interesting content. And we actually are doing some work sort of try to understand how that, and I don't have good results for that yet, but I think, but the leaning word, no, it's not, it wasn't done for it. And then for interpier, absolutely, I think we've done some separate work, some observational work, looking at high rates of deposition in some piers around here, and that seems to be the most likely fate for sediment which reaches down into the harbor. So the longer term, basically gets pushed up into these piers, it's a low stress, and can deposit there. That's not resolved in the model. We need to go to a much higher resolution. So that's still an open research topic which should be funded.
I don't know a question for you, but so we saw that sediment coming from the harbor and we thought, oh, it's all this clean watershed. You're telling us that also upriver, and what we saw was we extended stuff from the lower river, which is probably there 214. And do you know anything about nutrient concentrations that actually work? Oh, we thought it was clean once we were in today. We don't know what that means. Anybody know?
Yeah, no, I think the important point there is it's still a fairly thin layer that was resuspended in quarter centimeters, whereas you're looking at deposition of contaminated sediments, which I think my guess is the peak concentrations of contaminants are a lot deeper. So yes, you do have remobilization of that near surface sediment, but that's not to say you're digging down half a meter. So, but I don't have information on that.
Or is it just that we wait for the next big stuff?
Right.
And then all that big that
Well, absolutely. That's that same process. No, but that's what happens. I mean, that's
called capping.
I mean, yeah, that is what happens.
Jim, are there questions?
One, Robert wants to explain the difference between stress and stratification effects.
So stratification, essentially, it takes energy for the tides to mix stratification. So it's harder to mix a stratified water column than it is to mix unstratified water particles, stir it up, essentially lifting that salty water higher takes energy. And as a result, there's less energy to reach the bed. There's less stress on the bed. There's more loss of energy in the water column. And so consequently, you have, where it's stratified, lower bed stresses, less resuspension, and greater chance of deposition. Is that sufficient? Great.
Do you want to say, you mentioned before, Dave, that you had an estuary turbidity maximum around George Washington Bridge, and then you showed us another one in Haverstraw Bay. Do you want to comment on why we see these different ETMs in different systems?
Yeah, sure.
Two or more?
Yeah, actually, that's another talk, but I have another slide next. Can I still use this?
Yeah.
Well, so, yeah, I mean, I mentioned it briefly, but it all has to do with the salinity fronts. And so, essentially, you have this trapping at salinity fronts. And so, conceptually, people have always thought about the salinity front being between freshwater and a little bit of salt. So that's sort of 0 to 2 PSU transition, which is where you have this convergence associated with, estuary circulation going upstream and then river coming downstream. That same process, though, happens at any salinity front, so any gradient. And these salinity gradients are formed not just at the limit of the salinity intrusion, but they're formed due to bathymetry. So essentially, you have constrictions. Okay. And so, so what this is showing is up in Haverstraw Bay, where we had our observations here. This is showing a snapshot from the model, and this is the gray lines are the bathymetry. So it gets deep. This is Curtin Point. You have a constriction at Curtin Point. Haverstraw Bay, Tappan Zee is down here. And so the colored lines are salinity at the start of a flood tide, at a flat flood. So you see is there's a sharp gradient where saltier water is red associated with this constriction. Essentially, the water has to rush through there, and as it rushes through there, it expands, and salt can stay there, basically. Right? But you have a gradient in stratification. So this is just near bottom salinity. This near surface salinity is all about the same. And so you have stratified downstream of the front, unstratified upstream of the front. It's usually showing bottom stress. And so you see high stress where it's unstratified in shallow regions, and low stress back behind the front. That then corresponds with the gradient in suspended sediment concentration. So you have lots of resuspension upstream of the front in the high stress regions, very low concentrations, low resuspension. And you can see this convergence here where the velocity vectors are, it's going downstream at the bed, upstream from the front, and it's going upstream as you have that convergence associated with salinity intrusion. And then consequently, you get a lot of deposition. So the pink colors are erosion and the green colors are deposition. And so this is, I mentioned, a Haverstraw Bay. So yes, it's happening near the salinity intrusion limit, but it all has to do with that constriction. That's why it's there and not somewhere else. If you then look down in the lower estuary, the same thing happens. The George Washington Bridge is built there because it's a little bit narrower there than it is elsewhere. There's a big piece of bedrock there. And so that little constriction is enough to have the same process go on. It's a little bit, it's not as pretty in the sense it's laterally asymmetric, where the Salweg is over here on the right side, it's deeper over here on the right side. And so at this point, which is where the George Washington Bridge is, you have this front associated with that, higher salinities or different colors, but there's a gradient in stratification there, there's a gradient in stress there, high stress upstream, again, it's more of a lateral front than a longitudinal front. You have resuspension over on the shoals, and then you have this pattern of deposition behind the front and erosion behind on the other side. And that moves around sort of with the spring leaf cycle and tidal. Because this is a snapshot, but because you have this front, you have the ability to trap a lot of sediment there, which means you have a lot available to resuspend and make it easier. Great question. So,
do you think that the system is, so it seems like you went looking at the pressure to see if that's when the sediments get exported to the longer duration event, I guess. And that's what I would think might, occur, but you found it didn't occur still. So do you feel the system is just now a very good trapping Tidal river, and that you would be very unlikely to export things?
Well, so yeah, longer term, we think it's at equilibrium. So longer term, we think everything's sort of keeping up, and certainly there's evidence of that down in the estuary, where sort of long term, the rates of accumulation of sediment are the same as the rates of sea level rise, I think what might be missing from the model is that, we can constrain the volume flux pretty well, the concentration. So if you increase the concentration, for example, you increase the erodibility, because more sediment around, you could increase the erosion. And so the problem is that a pretty small number, you can tweak it, and it's and come up with a different answer. So I think absolutely it's longer term at equilibrium, and so it's happening during. I think what happens is exporting during sort of the moderate discharge events, during spring freshets, during sort of the annual sort of event, rather than really big events which are overloaded and a really low flow summer periods where there's not much flux.
So it's like a slow leak.
Yeah, that's right. And that's a problem. That's a hard thing to measure. You know.
How much does dredging account for relative to negligible?
Up there, it's not much. Up there, it's not much.
And last question is, how much do you think this has changed through this dam? Do you think that modifies the low heat intensity, and that might make things be better at exporting during an event? Do you think that that's having, changed the system, and if that hasn't occurred, then the system would have a different character, or it's really more about the system so flat that it would be hard to export?
I'm getting outside of what I know, but I don't think it's had a huge effect. There's one dam, I believe, on the surface, one of the New York City reservoirs, and it kind of stands out as relative to the other system, it didn't have much export of sediment, and I think that's probably because there's a lot of trapping of sediment behind the dam. And so, but that's a fairly small part of the total watershed. So I don't think it's had a big effect at the watershed scale, but certainly at the local scale, you can get, basically you'd have, in that case you have removal of sediment, but more transport capacity because the water is still going through. So in that case, that would tend to make it more of an export system.
The system had a lot of reservoir hydropower, or a lot of hydropower, but big flood control capacity like 1930s, and I don't really know the history well enough to say much more than that, but I know that there's a lot done, so it'd be interesting to learn how much that changed around that time, how much relative to sediment transport.
Yeah.
Speaking about climate change, where we're storms, and we're also expecting sea level rise. Is there anything out of the study that help us?
So the question was, how does climate change, think about these results in the context of climate change, sea level rise and storm frequency and magnitude and so forth. And so I think from the sea level rise perspective, it's actually, that's not the issue here, because there's an abundant supply of sediment. There's so much we have to dig it out all the time, maybe in the Corps of Engineers. And so there's plenty of sediment to keep up with sea level rise in the estuary and Tidal River. I think, and it is interesting to think about how the changes in the hydrology. So I think some predictions for around here are going to be a little bit wetter, but it's going to be a shift to more of a summertime rather than less of a spring freshet. Actually, so decreased spring freshet and more sort of winter storm, I think. And so that actually, that's a good question. I don't know if there's enough data out there to think about how sort of morph to one of the conceptual models for how a sediment system, if you load it up during the winter and then the first flush of the spring has higher concentration for certain discharge. If instead you had more winter storms, you might see that sediment moving through the system more on a continual basis. That might tend to sort of decrease residence times, I had to guess, but complete speculation. That's not fair.
In the areas where there are greater deposition sites, is that a threat to wetlands? And considering New York State has a zero wetland loss policy, might that mean more dredging to protect those wetlands?
It's great for wetlands. So wetlands love sediment. Wetlands need sediment to grow. Some mix, they grow with a mix of inorganic sediment, which is sediment comes from watershed, and organic, locally produced, like plant material. And so they need some minimum amount of fine sediment coming in. And so this is actually good news for the marginal wetlands.
So it doesn't ultimately fill in?
So plants keep going up. They keep sort of, as you put more sediment, they grow a little bit higher. So, so we come down to the estuary.
So accelerating the process of its ultimate transformation.
Yeah. It's interesting as you come down to the estuary, though, where you start to get into issues of, because a large amount of, there's not much wetland around here, just because of the geology of the system. It's not a big coastal plain. It's fjord, geologically constrained. But where there is wetlands, we start to wonder about sediment supply, how much sediment made it down here, how much sediment would perhaps get up into the estuary, or into the marginal wetlands of the estuary versus getting removed by dredging. So that certainly is a question as far as that, whether there's sufficient sediment to keep up.
You stated that sediment accumulations are currently the same rate as sea rise. Is that a fact? That's a question.
That was somebody else's conclusion. Yeah, Chris Summerfield has done some work, some coring, essentially showing that in the estuary itself.
Very maybe on average.
On average, sure. And so the important point being, a lot of the changes are associated with filling of the shallow regions, which constrains the channel, and you get scouring associated with that. So there's a lot bigger changes associated with local anthropogenic changes than with sea level rise.
Does your study enlighten us in any way in terms of GE dredging and capping upriver and how events like this may affect the results of that work?
No. I'm not enlightened at all. How can I touch that?
I think, but let me just, the answer is maybe. In fact, a lot of the sediment data is being incorporated into our old CART models to test. We're hopefully we're going to go back and see how well we did 10 years ago. And actually, what David mentioned earlier about having those gauges in place to pick up Irene and Lee was a result of the work we did on contaminants. We did find that those Catskill watersheds were yielding a lot more sediment than we thought, and we found that out through the CART. Now, how PCBs, I don't think what we're finding here affects further upriver, but it certainly will affect as the PCBs get over the dam and get associated with sediments and organic material. How much, we don't know, but we're going to try and look at that over the next couple of years. Anybody else? Frank?
So do you think that most of the, how much do you think of the sediment that was recovered? I really had thousands of things like several years passed by. I couldn't be innocent from your.
Yeah, I mean, I didn't put a number up there for good reason. I think, I mean, if you trust the fluxes we get sort of during the events, I think it's a fair bit in the past. Maybe half of what was up there immediately after. And again, so we had several years to work through it. You know, the annual type event is moving. Again, so if you just extrapolate that out, not none.
I have one follow-up to you. And your one slide that you showed the bed versus the input of sediments coming in, you had a blue for the bed sediments. When you got down to Haverstraw Bay, you were dominating. Dominant was the bed. Was that both upstream and downstream?
Yeah, it's everywhere. So what that is there's fine sediment which is in the bed of the tidal river estuary, which is being remobilized during the event, and so that same material then is being replaced by sediment from Irene and Lee. So.
All right. Well, thank you, David. A couple of notes. If you RSVP'd, great, we have you in the system. If you just walked off the street and came in for a cup of coffee, if you wouldn't mind signing into our log that should be up at the front desk and leave your email address so we can be in touch with you. And I'm glad PCBs came up for you PCB aficionados. Next month, which is a Wednesday, November 18th, we're going to hear from Steve Bersian, who's a toxicologist from Michigan State University, who's going to talk about PCB effects to mink. It's very, very interesting, some controversial findings. So hope to see you in a few weeks. Thank you very much.
Thank you.